Well, hello everybody, Dave here, and welcome to your first in a series of lessons on this idea of uniform circular motion. We're going to do our best to tie in circular motion to the linear motion that you've learned in previous physics exposure, and how they're similar and how they're different, but most importantly, how we can apply previous understandings of topics to this new topic in such a way that hopefully it makes it a little more straightforward. Now, the first thing we need to do is obviously define what do we mean by uniform circular motion. One of the things I think you've all figured out from physics by now is the fact that the way we can make it more challenging is to add different variables at play. Well, to make things fairly simplistic to start with when we're dealing with circular motion, we're going to define uniform circular motion as something that is traveling at a uniform speed in a circle of constant radius. If we have a changing radius or if we have a changing speed, there's other variables at play there that we're just not yet ready to deal with. There will be a time for that, but it's not right now. Now, let's take a look at this picture here of the car traveling around in a circle. Well, the question that I would always ask my class is, well, what do you feel when you're driving around in a circle? I typically talk about crazy drivers and how they just got their new license and they go around a corner way too quick, and what happens to your body? Well, everybody understands that you slam into the side of the door, but the question is, can you actually explain that using the principles of physics? And this is a classic misunderstanding that a lot of people have. They believe that because we have slammed into the side door, that there must be some sort of applied force taking place. And if you were studying physics back many decades ago, they would actually describe this as something called a centrifugal force, in that there was some sort of apparent force that caused you to fly into the door. This is no longer the case. We typically don't talk about anything to do with something called centrifugal force. However, when we do talk about the reason why we're flying into the door, the answer is simply because the universe changed around us. I always talk about relativity as being, what are you doing relative to the universe? What is the universe doing relatively to you? Well, if the car is traveling in a circle and your body didn't want to change that, remember Newton's first law states that an object in motion will remain in motion unless acted upon by some outside unbalanced force. So if the universe, which is the car, changes around you, the resulting motion of your body is not going to change instantaneously, so you're going to continue to travel straight while the car travels away from you. And the result is this apparent flinging into the door. So the reason why we feel this quote-unquote apparent force is actually due to the inertia of your body itself. So let's begin to redefine our kinematic quantities associated with motion. We know that our tangent speed is going to remain constant as we go around the circle, which means that there is actually no acceleration tangent to it as well. But does that mean that there's no acceleration, period? And the answer is absolutely not. If you take a look at the diagram here, as we move from point A to point B, do you see how the direction of the velocity vector is changing? Well, you'll remember from grade 11 physics that the only way you can change direction is if there is some sort of acceleration taking place, which means that for this direction of the velocity to change from up and to the right to down and to the right, there has to be some acceleration pointing against that motion. Okay, so we know that by definition then our acceleration is the change in velocity and change in time. Now, from here, we have to actually do a little bit of geometry and a little bit of an idea from calculus. Now, the first thing about geometry is to recognize the fact that we have a triangle where it's actually isosceles in that the two sides are the radius of the circle, and the distance in between point A and point B is actually, we're just going to call it delta S. Well, you see this isosceles triangle, and on its own it doesn't make much sense, but now if we do another triangle with the velocity vectors, something very interesting happens. We may recall from grade 11 that when we are changing velocity, that we're actually performing what's called vector subtraction. The idea that we are going to subtract the initial vector from the final vector. And so the second triangle you see in the bottom right there is actually us performing vector subtraction. We have our final vector, which is still pointing down and to the right, and we have our initial vector, which has been flipped and given a negative magnitude, and it's actually now pointing down and to the left. We know that because we are now performing vector subtraction, the difference between VF and VI is no longer going to be the total velocity. It's actually going to be the change in velocity, or delta V. Now, you'll notice that we have the angle labeled in both triangles. Because of that, we now know something very important. The first triangle, which dealt with the radii and the distance between the points, well, we said that that was an isosceles triangle. But we also know that the tangent speed itself is not changing over time, which means VF and VI, their magnitudes are actually going to be the same. And because of that, that bottom triangle is also an isosceles triangle. And because we have the angle that's also the same, we have what we remember from grade 8 to be a similar triangle. And because of that, we can come up with this equality that you can see in the bottom left, which is now delta V over V, it doesn't matter which V you pick because it's the same, has to be equivalent in magnitude to delta S over R. Now, it's not going to be delta V is equal to delta S and V is equal to R, no, but the ratio of delta V over V has to be equivalent to delta S over R, which is by definition what it means to be a similar triangle. So now that we have this equality, we have to understand why it applies to a circular path and not just a straight path like we have drawn. And for that, we have to understand this simple idea from calculus, which is now taking this angle and shrinking it down until it's infinitesimally small. You can see right now on that top diagram that we have an arc that is clearly above the line between points A and B, delta S. Well, that doesn't make sense then to say that that is a triangle because it's more of a actual segment of a circle itself. So how do we justify this use of this isosceles triangle? Well, for that, we keep shrinking down theta so it is so small that that arc length actually isn't discernible from a straight line. So imagine taking that triangle, make it smaller and smaller and smaller, and bring that angle in and in and in until it is so close that you could essentially say that it's a straight line. And so this is essentially the idea behind how we're allowed to use this similar triangle and these isosceles triangles, is the fact that we're just going to assume delta theta to be so small that essentially you can't tell the difference between the circle and the straight line between point A and B. But now we can take our expression for delta V over V is equal to delta S over R, and we can substitute that into our equation for acceleration. And when we do so, you can see something pretty awesome here. The first thing is recognizing that we have a delta S divided by delta T. Well, remember, we've just justified why we can use a straight line between points A and B instead of an arc length, which means that this is really just equivalent to our constant velocity equation that we learned in grade 11. And so if we substitute in V for delta S over delta T, what we end up with is this quantity acceleration is equal to V times V divided by R, or V squared over R. Folks, we have now derived what is known as the centripetal acceleration of an object moving in a circular path. Now, this word centripetal is important. We talked about this previous word centrifugal, but that's not a real force. That's just an apparent force. Centripetal accelerations and centripetal forces, these are the quantities that we're dealing with because they are always going to be pointing towards the center of the circle. If you remember back to our diagram where we had the changing direction in the velocity vectors, notice how in order to change it from up and to the right to down and to the right, you would have to have an acceleration pointing down and to the left. And guess what? That's pointing down and to the left right towards the center of that circular path. So from a geometry perspective, we were able to see it. Now from a mathematical perspective, we've actually defined it. Okay, so if we have an acceleration pointing towards the center of the circle, there has to be some sort of force pointing towards that because, again, Newton's second law states that an object will accelerate when a net force is present. So if we have a centripetal acceleration, there has to be a net force pointing towards the center of the circle. So let's go back and redefine Newton's second law. First, we know that F net is equal to ma, but now we have a different acceleration that we're playing with. We're playing with this centripetal acceleration, so let's substitute that in as AC. Well, guess what? When we're dealing with centripetal force, we're simply redefining Newton's second law, but in the case of radial directions. So we're going to talk about it going towards the center and away from the center. That's considered a radial direction. And so if we're talking about centripetal acceleration, then the net force radially in or away from the circle has to be equivalent to Fc, which is just equal to MAC. If we plug in our value for AC, we get the conventional definition of the centripetal force, which is equal to mv squared over r. So it should make sense right away, just from previous knowledge of Newton's laws, that if we have an acceleration pointing towards the center, it should make sense that the centripetal force, which is now equivalent to the net force in the radial direction, is also going to be pointing in that direction. There is no acceleration pointing away from the circle, otherwise that's the way the net force would point. So this is a really important thing to get used to early on, is we are dealing with Newton's laws, we are dealing with dynamics in the classical sense, except instead of dealing with things in a linear motion, we're going to deal with things in a radial motion towards and away from the center of the path. And so mv squared over r is something that we can use to calculate the centripetal force, but I don't ever want you to label centripetal force on any free body diagram as an actual measured force, because it's not. What it is the equivalent of the net force in a linear case. And so that brings us really to the tie-in between linear motion and circular motion. And when I teach the class, of course, I talk about it in terms of winners minus losers, because whatever direction the net force is pointing, that's the direction of the acceleration of the object. And so if we have more force pointing to the left than the right, then the acceleration will be to the left. The same thing holds true with circular motion, except now we're dealing with radial motion. So if we see that there's a force pointing towards the center of the circle, and there's a force pointing away from the center of the circle, then we're still going to deal with centripetal force the way that we dealt with net force in a linear case. We're going to take the winners, which are going to be all those forces pointing towards the center, and we're going to subtract from it the losers, which are all the forces pointing away from the center. And we know that that is always going to be equal to MAC, or mv squared over r. So this winners minus losers thing was a little trickier in linear motion, but with circular motion it's nice because we know that the acceleration is always pointing towards the center of the circle. So as long as you figure that out first, now it just comes down to what forces are pointing in that direction and what forces are pointing away. The spoiler alert I gave you at the bottom there is pretty clear in the point of this slide, which is the fact that we are dealing with the same thing. We've just redefined it according to certain notations. So now that we have the definitions, we can begin to ask the big questions that are going to help us solve circular motion questions. And the first and most important one is, which force is ultimately responsible for the object's circular path? And there's a variety of forces that we're going to talk about in this course that deal with circular motion, but specifically to this unit, the first three, static friction, tension, and gravity, are going to be the ones that we focus on. Now, static friction seems a little counterintuitive, being that the object is in motion, but remember that we're dealing with things that are radial in motion. Is it moving towards or away from the center of motion? And in this case, because we're maintaining a constant radius, the answer is absolutely not, which means that only static friction is present in the radial sense. If there was some kind of kinetic friction taking place radially, then the radius would be changing. We'd have a whole different discussion to deal with. We'll save that for another day. The second question we have to ask ourselves is the object interacting with the surface or not? Because if it is, then we're going to have a normal force, and if there is a normal force, what direction is it pointing, and does it actually matter? And so you may recall back in grade 11, you dealt with these things called elevator problems, which was this concept of apparent weight. The idea that because the universe was accelerating up or down, that actually changed the way that a scale would read your actual weight. So this is going to be the same with circular motion, because now we have an accelerating universe around these objects, which means that we're going to have acceleration that's going to point down or up or otherwise, which means that there could be some apparent weight discussions that we have to have here. The key thing to remember, no matter what, is that the force pointing towards the center is always winning. It is always the force that we consider winner, and we subtract the other forces that are considered losers. And the reason for that comes back again to Newton's second law, that for an object to accelerate, a net force must be present, and because we know the direction of the acceleration, we also know the direction of the winning force. So here are the typical scenarios that you see in circular motion. Please do not consider this a comprehensive list of potential scenarios, but it's certainly one that if you don't know how to do these ones, you've missed some of the basic understandings of circular motion. So for this lesson, we're actually going to deal with the first two in horizontal circles and vertical circles, and we're going to talk about the major difference, which of course is the fact that now the weight of the object may matter more in vertical circles because it's working directly against or with gravity. So let's start off with horizontal circles. And the key thing about horizontal circles is that we're going to have motion that is going to be parallel to the plane of the horizon. That just means flat. There's going to be no change in height, and FG is going to be at a right angle to the plane. And so we don't have anything that's sloped. We just have a nice flat surface, and we're going to move objects around in a horizontal circle. When this is the case, because FG is perpendicular to the surface, it is not included in your centripetal force discussions. You still may have to determine the normal force if we are discussing something like the friction at play. The classic questions involving horizontal circles is going to be something dealing with unbanked roads. That just means flat, where friction is going to be the only force present. Or we're going to have another classic, which is, as I had mentioned previously, this object spinning around in a circle right on a table where it's attached to a string that's put through the table, and there's this hanging mass perpendicular to the table underneath. These are the classic physics problems when we're dealing with horizontal circles. So let's take a look at an example dealing with horizontal circles. And we have this car here, which is a 1,200 kilogram car, and it's rounding a radius of 45 meters. Notice how they're giving you the coefficient of static friction, and that's because, again, radially the object's not moving towards or away from the center, so static friction makes sense. Don't get confused if they give you the coefficient of kinetic friction because they just want to drag that out of you by accident that you use the wrong one. What is the maximum speed that the car can have without skidding? So that's great, because for this to be true, all we have to do is find the speed at which centripetal motion is taking place. And so we know that the net force in a circular path is equivalent to the centripetal force. And the only force present that's causing it to stay in its path is the force of friction, and we know that this is always going to be equal to mv squared over r. Remember that this is exactly the same thing as when we deal with Newton's second law and say that it's always equal to ma. So from here we can solve for v, and you'll notice that in the solution for v, we've now substituted in the equation for the force of friction, which is mu Fn, but in this case we're going to use the coefficient of static friction because the radius is not changing one way or another, which means that it is static radially. So you have to use that static coefficient of friction, and you get a speed of 20.25 meters per second. Again, it's important to recognize that when we're dealing with circular motion, you will almost always be calculating speed, not velocity, even though our original derivation of centripetal acceleration involved velocity vectors. In practical applications of this stuff, you're typically going to be using just speed. Now, it's important to recognize this difference between static and kinetic. And again, it's just important to notice that the kinetic friction force is always going to be smaller than the static friction force. This is just the nature of friction itself. It takes more effort to get an object moving than it does to maintain its motion. Now, we have to watch out for this because there may be cases where we're talking about things tangent as well as things radially. So there may be discussions when kinetic friction matters. If you come into one of these questions where it asks for what is the maximum speed such that it doesn't change its shape, this is really asking for what is its maximum speed before kinetic friction would now be present because the object would be sliding away. And so the moral of this story, and this is why we're presenting it now, is just when you're driving in bad weather and it's rainy or it's snowy and it's icy, the whole reason that they want you to slow down is because the coefficient of friction has changed between the tires and the surface, and you have to account for that by slowing it down. Example 2, again, is another one of those examples that you're going to see come up quite a bit. And it's a picture that looks like this. And in this case, you have a puck that's traveling around in a circle, and there's this hole through the table and this hanging mass hanging underneath. Well, you may recall that when we're dealing with something that is static, and in this case, that hanging mass has been defined as not moving. It's suspended in equilibrium, which means that the force down has to equal the force up. So this is really telling you what the tension of the string is. But what also we're going to be able to figure out is how that tension now plays a role into the moving puck itself. So the three typical things that are asked are what is the tension in the string, what is the horizontal force acting on the puck, and what is the speed of the puck itself. So for A here, we don't want to overthink this too much. We know that the hanging mass is in equilibrium, which means that the force up has to equal the force down. That means that the tension in the string is actually equivalent to the weight of the hanging mass itself. You'll notice how we're not talking about the orbiting puck yet. So when we're going to calculate the tension, then it's just a Newton's law question where the tension is equal to Fg2, which is equal to 9.8 newtons. And with B, it's an even easier question now because we've already calculated the tension. We know that the only force that is causing this puck to stay in its path is the force of tension, because they tell you that it's a frictionless horizontal table, which means the only horizontal force that can be present is the force of tension. Well, we've already calculated the tension from A, so we can still use the same quantity now. This is very similar to the system of mass problems that we used to do in grade 11, when the tension was the same on the hanging mass as it was on the other mass that was being accelerated by that hanging mass. This is in a equilibrium position, which means that the tension on the hanging mass has to be the same as the tension on the puck itself. And once we have the tension, C is really straightforward because we can simply recognize the fact that once we have the tension, the centripetal force in this case has to be equivalent to that tension because it's the reason that it's maintaining its circular path. We know that the centripetal force is always equal to mv squared over r. In this case, we're going to use the mass of the puck because that is the object that's actually in orbit. You solve for v as we've done below, and you can see that we get a value for speed of 6.26 meters per second. So a very classic question that we need to understand. So with vertical circles, instead of dealing with something that's parallel to the plane of the horizon, we're going to deal with something that's perpendicular. And all that means is when you're swinging it, you're going to swing it vertically such that it's going to change height, and Fg is now going to be a factor. And so it's important to remember again that Fg is sometimes going to point in the same direction as the centripetal acceleration, and sometimes it's going to point against the centripetal acceleration. That's just depending upon where it is in its path. The key thing to remember, though, is that Fg is always pointing down. So no matter what, make sure you draw that Fg pointing down, whether it's towards the center or away. When we deal with these questions, the classics are going to deal with vertical roller coaster loops. We're going to deal with things that are on a string, and we're going to deal with driving over hills, which may not necessarily feel like a circular motion problem, but as we demonstrate it, you're going to see that it is obviously going to be a change in height, and it's going to be a question that involves this centripetal acceleration pointing towards the center. So let's do one of the classic questions here, which is going to be a ball on a string being swung around vertically. And we're given that the maximum tension of this 0.5 meter string can be 14 newtons, and then they ask you what is the maximum speed that the ball can have at the top or the bottom. The first and most important thing I want you to recognize here is the free body diagram at the top and at the bottom. You can see that at the top, both forces of tension and gravity are pointing towards the center, and at the bottom, the force of tension is still pointing towards the center because it's responsible for its path, but Fg is pointing down as it should. What this means is we're now into the apparent weight type scenarios that you dealt with elevators last year, which means that we should have different speeds that we can get maximum at the top and at the bottom. So when we calculate at the top, we know that the centripetal force is equivalent to the net force in the radial sense. And we know that both gravity and tension are pointing in that direction, which means that Fc is equal to Fg plus Ft. And much like all other Newton's laws questions that we've dealt with, that's still going to be equal to ma, or in this case, mv squared over r. When you solve this equation for v, we get a speed of 5.74 meters per second. If we calculate the bottom now, we can see that the diagram showed us that Fg is actually pointing away from the center this time, which means that when we were finding the net force radially, Ft is still pointing towards the center, but Fg is pointing away from the center, so we have a winners minus losers scenario here. And as always, it's equal to mv squared over r. When we plug all the values in and we get our answer for our speed, we see that the speed is actually slower than the speed that we had at the top. And the reason for that is now Fg is actually working against this maximum tension, which means that it's going to have a smaller speed that it can withstand before it will actually break. And so the fact that Fg was pointing in the same direction as tension last time meant that it actually wasn't hurting the string's chances at withstanding that speed, so it could go a faster speed as a result. This is an important relationship to notice when you do a question like this. Let's take a look at an example now that deals with a roller coaster. And in this case, it's going to feel very similar to the question that we just did, with the exception of the fact that now there's a normal force present, because you can see that we are sitting in a chair. And if we're sitting in a chair, that means that there's an interaction between us and the chair, or the car and the track itself. And so a roller coaster is moving with a radius of r. What speed must it have so that it just makes it over the top? That's important language. What speed will the car subsequently have at the bottom? And then what is the normal force on the passenger at the bottom of the loop if the loop has a radius of 10 meters? So this is a nice question that answers the question, why do I feel different when I'm in a roller coaster? You've all been on a roller coaster before, hopefully, and you know that when you go over the hill just barely and then you plummet towards the bottom, when you get to the bottom and you curve to go back up, you feel really, really heavy. And the reason for that is going to become apparent very quickly. The same thing's true when you go over a hill really fast. When you go over a hill really fast, you feel kind of funny, as if you're almost going to float. And that should make sense too, just based on an inertia discussion, but as well as this discussion of apparent weight given the circular motion of the cars itself. So let's deal with A, and the speed that it must have to just get over. This is a limiting case. And the limiting case is to just get over the top. That means that your normal force is approaching zero. And so what we want to do is we essentially equate it to zero and deal with Fc being equivalent to Fg. This doesn't mean you're falling out of the car. It means that you are at the slowest possible speed to go over without falling out of the car. If you went any slower than that, you either wouldn't be able to do the complete loop, or you would fall out of the car because there wouldn't be enough of this motion to keep your body in the car. And so when we have this, we have an equation for speed, which is v is equal to the square root of gr. This is a classic equation that you're going to have to derive given the scenario of a roller coaster. Don't always assume that it's going to be something that's just getting over the top, because it may be a question like what we just had with the ball and the string. But if it is just going over the top, this is the equation that we could use in order to calculate the minimum speed. One thing I want to note, and this is something that's important about physics derivations in general, we know that g is 9.8 or 9.81 or whatever you want to put it, but you typically want to leave it as g if it's a derivation type question. If it's a calculation type question, then absolutely you put it in, but until you have to do so, please leave it as g. So now we can get what the speed is at the bottom, given that we have that initial speed at the top, whatever speed that may be. So for that, we have to go to a conservation of energy discussion. And you'll remember that with conservation of energy, we're going to deal with this in terms of potential and kinetic energy. Now, there's no discussion of friction here, so we don't have to worry about energy being lost to heat or anything like that. And there may be questions that that's the case. But for this one, we don't have to, which means we know our initial and final energies are the same. We know that initially we have some kinetic and some potential, and finally we have some kinetic and potential, and then we substitute in our equations for kinetic and potential energy. Now, this is where it's important to be intelligent about our selections. We remember, hopefully, that our zero potential line is something that we control. It is an arbitrary point that we pick, and we measure all of our heights and whatnot from it. So for me, I'm going to pick the bottom of the loop to be my height is equal to zero. And what that means is that mgh final is going to be zero, because we're going to say that all of the initial energy has been converted into kinetic energy at the bottom from whatever height above that bottom we started from. And so you can see on the left-hand side there, our v at the top, well, we have an equation for that from A. And we can substitute that in to get this quantity gr. And if we look at plus mgh well, the initial height, because we called the bottom 0, we're actually 2 radii above to get to the maximum height above, which means I can substitute in 2r for h. And what you can see there is we have a very fancy looking equation for the speed at the bottom that is again in terms of g and r. And so this is a nice strategy when we're doing derivations, is if you can substitute in previously derived equations to give you new derived equations based upon those same quantities, then life is good. You're going to see a lot in AP forums that we're going to deal a lot with derivation type problems, so it's a good skill to start to develop. And for C, then, we can apply the same strategy, and we're just looking for the normal force on the passenger at the bottom. Well, again, we go to our definition of centripetal force, and we know that the normal force at the bottom is pointing up towards the center of the circle. We know that FG is always pointing down away from the center in this case. And we know that if we solve for Fn, we can now substitute in our equations for Fc and Fg. Now notice what I'm doing with the speed at the bottom again. I'm substituting in that quantity that I derived from the previous question. And what that's doing is it's making my final answer very neat and tidy. Because what happens? Well, R cancels and all we have is the normal force in terms of mg. So what this is showing you is that if your weight were mg, the normal force that is pointing up towards the center is actually equivalent to 6 times that, which is an interesting thing, and it is why you feel heavier when you're at the bottom of a roller coaster. So folks, that's a big lesson, but it's an important lesson in dealing with centripetal acceleration, centripetal force, and this idea of uniform circular motion as a whole. Coming up is going to be some application type lessons, and then we're going to get into gravitation. But I would strongly encourage you to take a lot of time on this lesson and really try to make sense conceptually why things are the way they are and how we can go about solving questions involving horizontal and vertical circles. Best of luck, and we will see you again.